All right, may the Lord be with you, and welcome back to physics lab number 2, and we're going to be heading into lab number 5, which is called resistive circuits. So, not to bore you, in making the experiment just like the capacitor lab you just completed, we're going to tune things up a little bit, and we're going to build a circuit that you can't use the rules for series and parallel and simply come up with the equivalent resistance in this case. But we're going to have to use a little bit more advanced model called Kirchhoff's rules to solve for this particular circuit. We're going to be looking at resistors. Resistors do not store charge. Capacitors do that. What resistors do is they turn electric potential energy into heat and light. So it resists the flow of electricity, and what basically happens is when the electrons hit the material the resistor is made out of, the resistor is a poor conductor, so there's a lot of extra collisions that take place in order to get through the material. And every time it collides with the material, it loses some of its kinetic energy and turns it into heat and light. So it heats up the material. It turns out that when you heat up a resistor, generally its resistance goes up. So you can keep that in mind when you're thinking about a little error in the experiment. We are using an experiment where our resistors are so big and our voltages are so small that we're really not going to see any big change in temperature. It's happening, but not at a big level. But it turns out the hotter a resistor gets, the more difficult it is to get through the material, because now the atoms are going like this instead of like that. So when the electron comes in, it gets knocked more when the resistor is hot. Okay? So it turns out, when you flip a light switch on and you turn on a light bulb, it's actually brightest in the very, very beginning. And if you look at a light bulb carefully, you'll see it'll get a little bit dimmer. And once it gets to its operating temperature, which is around 3,000 degrees, then it'll glow at that brightness corresponding to the resistance for that temperature. All right, so keep your eyes peeled for that. Anyway, this is a picture of all different kinds of resistors. And they got this thermistor right here actually allows you to measure temperature. And there's a trim pot here. This is a variable resistor. This is another resistor. It's called a rheostat. That's a dimmer switch that you'd have in your dining room so you can change the lighting by turning the little knob. Potentiometer does the same thing. It's just hooked up a little differently. We're using your standard resistor up here and for our experiment. And you'll notice it got like a little color code on there. And the color code gives you the value of the resistance. It gives you the two numbers in the resistor value and then the power of 10. And it follows the colors of the rainbow. It goes black, brown, and then it goes Roy G. Biv. And once it ggets to Biv, which ends in violet, then it goes to gray and white, and it covers all the numbers from 0 to 9. Okay, so the first two colors are the digits, and then the last color is the power of 10. So if you had like red and black, so you'd have black, brown, red, so that number would be 0, 1, 2, woo, watch it there, 0, 1, 2, and then what did I say the other color was? Red, and then black. Black is 0, so it'd be 20, and then let's say the third color was red again, and that would be power 2. So that resistor would have a value of 20 times 100, which is equal to 2,000. Okay? So 2,000, would that be that value of the resistor? Okay. Now, in our experiment, we're going to hook up a battery. So I got my symbols over here. This is a resistor symbol. Here's the battery symbol again, and these are the connecting wires. So whenever you see black lines, those are your leads that are connecting everything together. Okay? And we're going to come out of the battery here. We're going to go up here. We're going to split. You're going to split up here to R3 and over here to R1. But then notice this guy right here. So when you get here, the electricity, the current could split, go down this way or go straight. In fact, it could do that. Or this electricity here hits this point and it could go up this way and go straight. So which way is it going to go through here? Well, it depends which one has more power, how much one has more voltage when it gets to this point over here. So the more voltage, it'll push it this way. More voltage, it'll push it that way. Okay? So this is a much different circuit than our capacitive circuit. Then it goes over here to R4, R2, comes together, and then goes home. Now, Kirchhoff's rules, there's two of them. The first one is called the Junction Rule. And it says that all the current flowing into a junction must equal all the current that's exiting that junction. So if I go back to this picture again, when this current comes up, it'll split. Part of it will go this way, and part of it will go that way. So all this current going into the junction must equal the current coming out of it. All right, you get to this point here, the current would be flowing like this, and if current was flowing up like this, you'd have this current going in and this current going in. So these two added together would give you this current right here. Now, if the current went and flowed this way, because this was stronger, then this current going into that junction would be equal to the current coming out in those two directions. Okay, so that's what the junction rule says. And you can see in our circuit here, we got one junction here, another junction here, and a fourth junction right there. Now it turns out when you have three regions, you can see we actually have four regions, but three enclosed regions, okay, and then there's a region on the outside like that. You can go all the way around the outside. I usually that's how many equations you're going to need. So to solve this problem, since we have three enclosed regions, we only need three equations. All right. Now, the next equation says if you go around a loop, all the voltages have to add up to 0. So if you go around the loop, all the voltages have to add up to 0. So if we go back to that picture again, so if we pick this loop right here, the voltage right here, the electrons come out with all that voltage, and they come down here, and then they drop it, and then they drop it, and then you see you're back home 0. So that loop is easy to understand because this is a positive voltage right here, and then you lose voltage, you lose energy per coulomb when you go through a resistor, and then you go through the second resistor, and that all adds up to 0. Now, here's a kicker. When you go in this loop here, notice there's not a battery. So how's that going to add up to 0? Well, the current's flowing this way. So if you go around the loop this way, this would be a drop. But let's suppose that as we come up here, see, we got to go this way now. But generally, current's flowing through R4 in this direction. So when you go through this one, the voltage is actually going up. So you'd have this drop plus this rise, and then depending when you close the loop, so you got to pick one direction. So we go like this is a drop, this would be a rise, and then what's going on here? Well, as we said before, if this side was more powerful, current could go this way, and if this side was more powerful, current could go that way. So when you get to this point, let's say the current's flowing that way. All right, well, you're going like this, so you see it's not a drop, it's a rise. So these two positive voltages would add up to this voltage, negative, and then it would be equal to 0. Incredible, huh? All right. and that's called Kirchhoff's loops. Now once again, there's one loop here, one loop here, one loop here, and then there's also a loop if you go all the way around the outside. All right, great. So now we're going to put this to work and just show you basically how that works out. Now the equation we're going to use, voltage is equal to current times resistance. Now we're going to be doing this a lot in lecture. So this whole analysis will be duplicated on the PowerPoints in lecture because it is a little bit complicated, and so you need to see it a couple times. And then you actually do it in the lab, which really helps to solidify things. So let me move this little thing out of the way right here so we can see all the equations. And basically, what you do is you take 3 loops, and you take, like if you're working on with pencil and paper, you draw your loop. Now there's only one battery in this whole circuit, and it's right here. So current comes, conventional current comes out of the positive and goes to the negative, thanks to Ben Franklin. Now you know, electrons really go this way, but it doesn't matter. Whether you got positive charge going this way or negative charge going that way, they're still delivering the same energy to the circuit. So we just go with Ben Franklin, and so we draw a loop like that. And then up here you can draw the loop either way you want. My guess is that current is going to flow down like that. That would be my guess. Okay? On this side I got it going down like this. Then on this other side I got it going up like that. But you can pick whatever direction you want. The math will work out. Okay. So here's what we do. We go on this A current. We're going to write down a current loop for A. And we're using Kirchhoff's loop rule. So you see voltage, and then this can be the voltage right here, and then the voltage right here. And remember, V equals IR. V equals IR. So when you're in this R1 resistor right here, okay, so here's R1 resistor right here. It could have current going through it from IA, but it could also have current going through it this way from IB, depending on how powerful the IB current is. So we put those two together and we write down V in that first resistor, 1, is going to be equal to IA minus IB. Because as you can see in the picture, times the resistor, R1. Because you can see in the picture right here, R1 is a resistor, IB is going backwards compared to here. So current's going into the resistor in IA, but it's coming back IB. So you need a minus sign. Okay, same thing over here. You see the IC is going back while the IA current goes forward. So there's 2 pieces for the resistors and then 1 for the battery. So I put the battery on the left side and equals IA minus IB R1 plus, and then for the second resistor, IA minus IC, because remember, C is going backwards, times R2. That is Kirchhoff's 2 rules put together in one statement. Okay, it's called the mesh method. It's called Kirchhoff's mesh method. We're meshing the 2 rules together. One more. We'll do one more here. And this guy right here, we're going to be in that loop. So you see when we go through this resistor now, B is in the positive direction, current's going this way, and A is going the other way. So you see, and there's no battery in this loop. See, no battery. And so 0 is over on the left side, no battery, equals IB minus IA, R1. So notice it's just the opposite of this guy. Plus, in the middle one, we've got IB positive, IC is going the opposite direction. And so that's IB minus IC times R5. And then down up on the top, there's only one current going through R3, and that's IB. And you can see this guy is exactly like that guy, and that's this equation right here. Now you got to collect all like terms, so these 3 equations are right here. Now in the experiment, you measure the resistor values and you pick the voltage, and then you can determine the currents. All right? So you got R1, R2, R3, R4, R5. You plug them in the equation, and then you put in your voltage, and you solve these three equations simultaneously. That is not fun. You don't want to do that by hand. Don't do it by hand. There's a website, and it's on the lab sheet, that'll do it for you. It's done by Penn State, and all you do is you plug in your numbers, and it'll solve your three equations simultaneously for you in about a microsecond. Done. Okay. Now, you're going to do the experiment. Can I go over here? Yeah. Okay. You're going to do the experiment in MultiSim. And you can see the exact same arrangement right here. There's your 5 resistors, there's your battery. You can measure the current right here. So this is a current meter. So current coming out, okay? There's another current meter right here. You can measure that current. And then you can move these guys. So you pull them out, and then you can put it over here and measure the current here, put over here, measure the current, put up here, measure the current, and so on. But for the experimental part, you'll just have one current meter. And that'll be going to these 5 resistors that are your REQ, your equivalent resistance. All right? That'll be your equivalent resistance. So much current will come out of the battery depending on how much resistance is out here. So you'll do 10 measurements, just measuring the current right here and setting the voltage right there. Now remember to give your voltage like 3 sig figs. You can give it 4. Don't give it much more than that. All you do is double click on that thing. Don't forget you need a ground right there. Now this voltmeter right here, you have to connect it, and then you got to disconnect it, put it over here, measure it, put over here, measure it, over here, over here. Now this is interesting. You got to keep track, because if current's flowing this way, it'll be a drop like that. But if current's flowing that way, it'll be a drop upwards. So in one case, the voltage will be negative, in the other case, the voltage will be positive. So keep an eye on that when you make that measurement. All right, let me see what the next slide is. Okay, so anyway, this sim setup, and we'll be going through that in class. And and one last thing. When you're all done with the experiment, you're going to take that resistor R5 out of the circuit and put another battery right in there. And then all you're going to do is measure the voltage across R1 right there. You see the letter A and the letter B. So you're going to measure the voltage across here, right here. So by the way, any wire that's in contact has the same voltage. So you see all this wire is connected all along here. So you can put your voltage probe right here and then touch right here. Okay, and that'd be the voltage across AB. It's called voltage AB. All right, you're going to do that for the first experiment, and then you're going to do it when you change that R5 to a battery. So now you're going to have 2 batteries in the circuit, and then you're going to redo Kirchhoff's rules, put it into the 3 unknown equation solver, and then see experimentally what you get. Now the one bad thing about MultiSim, it's perfect. So you're not going to get any error. So if you do get an error, you know you messed up with your mathematics, because MultiSim is perfect. That's the only bad thing about simulations, this particular simulation. All right, so we're all done with the introduction part, and we're going to show you how to do the experiment in real life, and then you'll get to do it in virtual cyberspace. Okay, so over and out for part 1.